we're trying to get a little bit better sound on the tape today. So there will be a wireless mic. And without further ado, I'd like to introduce Bill Ragsdale, the first speaker. If you need to know who he is, look on the Who's Who in Fourth on the website. A little bit more about that later.
Okay, mic adequate? Well, Charles Moore, glad to see you here, and other distinguished guests. It's a real pleasure to be here today. Let me kick off the slides. I've got a 43-second time per slide to fill the time slots here, so we'll see how that works out. I had to give this talk a few days ago in 5 minutes. I took a 40-minute talk to 5 minutes, and I found out I should have timed the slides. We're going to talk about fox hunting or bunny hunting in amateur radio. It's amateur radio direction finding. It's a hobby within the amateur radio community. It has some functional purposes, like trying to locate a jammer or try to locate someone who's abusing amateur radio or radio privileges. So it's partly fun and it's partly work. There are generally about 4 methods that are used to locate a distant transmitter, an unknown transmitter. The first is just basically signal strength. The closer you get, the higher the signal level. The next is the directional antenna, which can use triangulation. It is very, very popular. One that is quite precise is dual antenna nulling. They set up an antenna pair, switch between the antennas, and they set up a very precise cardioid pattern with a null in the middle. And finally, the method that is used most widely on the West Coast is multiple antenna phase detection. In the East Coast, they seem to use directional antennas more. In the West Coast, my experience has been a little bit more on multiple antennas. So this is the classical direction finding by triangulation. There's a monthly fox hunt, bunny hunt starting in Fremont up on a big hilltop on Zapotec Boulevard. Goes over the whole arc of the Bay Area from northern San Jose all the way up to Hayward. So off the top of the hill, you take a directional antenna, and we set one bearing up and extend it out into the salt flats, which is number 1. About 20 minutes later, we drive down here. We take bearing number 2 right here, drive around some more, take bearing number 3, and then the target is in the middle. Then you go in the middle, and then you kind of hunt physically or try to narrow it down. It turns out I have been very unsuccessful with this method. It's a bulky antenna. You got to get it out of the car. You do a setup. It takes 3, 4, 5, 6 minutes. Then you drive, and you've got to get the gear in and out of the car, out of the car. I have yet to find the bunny within the time period. Normally, everybody else has found it in an hour, hour and a half, and they go for coffee at McDonald's and leave me still stomping around the salt flat. So I needed better hardware. So phase detection, the way that's done is typically with 4 antennas that go into an FM receiver. Well, the receiver looks about like, it's a handheld HT, handy-talkie, handheld transceiver. You put an adapter on the front end of it to give you a display coming in from 4 antennas. The idea is you scan the antennas at a 500 hertz rate. You reconstruct the sine wave, you determine the direction by the phase delay, and then you make a directional display. We'll see each of these in detail. The designs, back in the 1980s, there's about 15 integrated circuits. The next generation in the 90s was 3 processors, 2 general purpose processors, and one was a digital signal processor. And then finally, I come up with one which is just a single chip. It's just a 1-chip design.
Here's the example he's talking about. You want to see it?
Yeah, excellent, very good. Okay, so here's how it works. The theory is you got your handy-talkie transmitter. It's an FM receiver. If you move it away from the signal source, the apparent frequency lowers. This is good old Doppler shift. If you move it toward the frequency source, the frequency increases. So the idea is you will virtually move that antenna back and forth. You'll move it to and from the transmitter, and the idea is the speed of light, the transit time from antenna to antenna, will give you an indication of the direction. So the way you can do is you can spin the antenna. You put the antenna on a bicycle wheel and spin it around at 500 revolutions a second. You will get a 500 hertz audio signal. You can process from that. There is a problem. That is 30,000 RPM. As we know, most hand grinders go at around 30,000 RPM, and of course the antenna is going to fly apart. So the alternative is we take 4 antennas, we switch between them. So as we switch between antenna A, B, C, D, A, B, C, D, we get the equivalent of rotating the antenna. We get an input sine wave and then sample the sine wave 4 times. Each time we switch antennas, we take another sample. And we develop a piecewise linear approximation of the sine wave. Due to audio roll-offs in the HT, you get a little bit closer to an actual sine wave. So we have 4 input samples. Every time we switch an antenna, we wait a little bit for it to stabilize, and then we take a sample, an analog to digital sample. So with the lead antenna, angle 0, we get this reading. With antenna A, this would be antenna B, antenna C, antenna D. Each of them has an unknown phase shift, which is the angle offset to the unknown transmitter, and an input amplitude. So we have 3 equations and 2 unknowns, and that's the task, how to solve that. Well, there's a number of ways. The complicated ways, which are very general, very powerful, is the genetic search or genetic algorithm. It takes a lot of memory. It works with a large number of variables, and it's more appropriate when you don't have a well-characterized model. Well, in our case, we have an extremely well-characterized model. In other words, we know what that waveform really ought to look like, and so we can use simpler methods. Matrix algebra is appropriate for solving linear equations with several unknowns. However, the math is complex and takes more memory. Now, remember, we're going to be working on a PIC processor, and we end up with about 48 bytes of memory that's usable. So we got to be very memory conscious. Neural network, another technology, very general, good, again, when you have multiple models and you're a little uncertain of your model characteristics. And then the final one, the one I actually use, is plain old least squares solution. So the way it works is we have input samples. So from antenna A, B, C, and D, we have 4 input samples. We generate internally a hypothetical sine wave at 4 intervals. And we initialize it just saying 0 angle and an amplitude of sort of a unity amplitude. And then compute the difference between the input measurement and our internal model. So that's the input sample and the model for antenna A, input versus model B, C, D. Take the differences, square them, and sum them. I tried several different other simplified approaches to this, initially using a spreadsheet. Took a plain old Excel spreadsheet, developed 3 different models, and found out that, sure enough, least squares is the one that really works the best. So here is the least squares model done in 4th. The input value, this is for emulation, for testing. So we have an input angle, and the angles go from 0 to 15, which corresponds between 0 and whatever 22.5 degrees less 360 is. So angle 8 would be 180 degrees. The input scale, 128, happens to be input scale of half scale. From this, we synthesize some theoretical raw analog to digital inputs. So if we're sampling at 90, 180, 270, and 360, actually no, it's 0, 90, 180, 270. These are our digitized inputs. We then run through a simple infinite impulse response digital filter, simply exponential smoothing, and generate some stable internal values. We spin the antenna electronically 100 revolutions, which is 0.2 of a second, and then stop the process. Then the work starts. We assume an input gain, an input gain, and an input phase. Calculate the prior model and the current model, input and the input values and the calculated values, and then calculate. Well, these are using the prior models, the current, the prior version parameters, the current parameters, and generate the estimate for the next iteration. So in this case, the gain is going to go from 66 to 63. The phase is going to go from 8 to 9. Then those are fed back to the current values. The prior values are saved, and we integrate once more. Spin the antennas another 100 times, go through the loop one more time. What we end up with are the errors. These are the least squared errors, and we're trying to minimize these 2 particular numbers. the error in and the error from the model. From that, we developed the LED pattern, which currently the best guess is 8, which is 180 degrees. And down here is a little picture of what the LEDs would look like. And sure enough, from the southern direction, this LED is illuminated. We'll see how the LEDs are set up later on. We also have an overload count. If the input signal gets out of range, we put an alarm signal as a display to the operator to turn the gain down from the receiver slightly. We try to bracket the gain. We have a 8-to-1 amplitude spread in gain. It turns out the model values themselves do not have to reside in memory. We compute all the values on the fly. So really all we're doing is holding these values in memory, these values in memory, and the errors. And the model values are only shown for convenience in testing and development. So to optimize, we alter the gain and alter the phase by essentially unity amounts. If the error decreases, continue. If the error increases, then reverse the change. The gain is limited over a range of 1 to 8. Report the overload. Show the display on the LEDs, and just do it over and over again. And the optimization inside says that if you start up with this particular gain in phase, make the calculation of a change of gain, a change of phase, and this is the ideal value, but you don't know it when you reach it, because all you've known is that your error improved. So it makes another estimate down to this point, finds out that the errors have increased, so it reverses the changes, comes back to equilibrium again, but again doesn't realize that that is necessarily ultimate, so it makes the loop back up to here. So in this case, you make a figure-8 pattern around optimum. If your scaling happens to be that you never reach optimum, you end up walking a little circle around what the optimum value is. And the directional display. A lot of these direction finders use 16 to 32 LEDs from a display. I want something that's handheld. The goal on my direction finding unit is it's the same size as the handy-talkie. So I want a box that's about 3 inches square. In that case, I'm only using 8 LEDs. But I can display 16 angles. So if the calculation comes directly at 45 degrees, then I would illuminate that particular LED. If it's at 68 degrees, I illuminate the 2 LEDs, which says it's halfway in between. If I get to 90 degrees, then I would illuminate the single LED. So again, I'm able to squeeze more information out. Also, I'm port restricted on the microprocessor, and the microprocessor drives the LEDs directly, so it's nice to have a smaller number of LEDs. Oh, the issues I encountered along the way. These are kind of typical of any small project. It's a display complexity, trying to minimize the size of the hardware and the complexity of the display. Likewise, living within about a 48-byte RAM memory limitation. The complexity of the processor, there's a 3 generations of PIC, or 3 PIC families of processor. I'm in the mid-range, which is it's kind of simple and adequate. It has a couple limits which we'll meet in a moment. The programming language, originally I was going to do PIC assembler, and I was going to do some sort of debugging and testing and forth. And the more I got into it, the less I wanted to use the classical PIC assembly language. And because I've debugged, raw classical assembler, and especially if you don't have a very good debug facilities, it can be quite burdensome. So I fell back onto what I was comfortable with, which was Forth, and it's worked out very well. Complexity of calculations came along the way. I have a multiply and divide. I don't have a square root. I don't generate sine cosines by calculation. I have a simple lookup table. And lookups are a little bit tricky with a PIC processor, but it works out fairly straightforward. And finally, scaling. I have a wide range of scale. Most variables are byte size. Several of them are word size. And the least squared errors are double word size. They're 32-bit variables. So I have 32-bit math aboard and a lot of comparison operators that will work on any of them. I developed the tools from scratch, and that's the bulk of the project. The core development of the application was probably 6 hours, and the development of the substructure that made everything work was about 3 months of aggressive part-time. It was kind of like all the spare time for about 3 months. I did 3 generations of emulation on Excel spreadsheet. got familiar with the processor, and then did it. I had done actually a PIC assembler several years ago, so I pulled the guts out of my PIC assembler and then wrote an emulator so it emulates synthesizing the PIC memory space on a PC. And now I've written a classical assembler that will take the fourth high level, and it generates legal, classical, published PIC assembly and a hex loader. So for kind of final error check and debug, you can sit there and you can look at assembly code every single byte in the application. The implementation is subroutine threaded code. The 7F, 16F series on the PIC processor does not allow access to the machine stack at all. It's a Harvard architecture, and you have essentially no access. You have, well, almost no access at all to program memory space. And there are ways to play games with the program counter, but I just didn't want to get involved with any of that. And so I just used straight subroutine threaded code. The value is that I can intermix high level and assembler. So I have a set of assembly level conditionals, if then else, begin, while, repeat, and so on. Then I have a high level set. The assembly level set willing conditions come off the machine status register, and the high level ones come off the fourth stack. So I can write, and you'll see later, we can write 3 or 4 lines of code and then go right straight inline fourth. The data stack is 16 numbers, 10 numbers deep, 16-bit values. The loop stack, I don't call it a return stack because it's only there for temporary storage and for loop parameters. Because again, I don't need it for control purposes, only for loop and temporaries. It's 8 words deep. I cache the top 2 stack words. So top of stack and second on stack are in registers, so you can speed up arithmetic calculations. And then when they're full, they automatically overflows into stack. 48 bytes of application RAM, and right now, tethered into a development system, I don't have fourth interactivity live into my development hardware. That may come along in time. So the support. This is all developed on Andrew McEwen and Tom Zimmer's Win32 fourth. I've had it on my computer for 10 years or something like that. It is a dream to work with. The documentation is, I would rate it as, barely adequate. It's enough to, if you really know fourth real well, you can figure out what's going on. It's extremely rich in functionality, extremely rich. And anytime I look for something I wish I had, if I look hard enough, I find it in there. I just don't find any documentation that says what it's about. So I got to go read the source code to figure out how this sucker works. Andy?
Are you using the OOP aspects of it, or just straightforward?
No, I haven't gotten into the object-oriented programming. This is just plain vanilla fourth. I haven't figured, there's something like 6,000 calls to the Windows operating system, which I haven't figured out how to use. I don't know. So it's plain vanilla.
That's all right. Neither is Microsoft.
Okay. Yes.
I just want to mention,
John. Good.
there is a users group, I think it's Win32 Words at Yahoo or something like that. You can get your answers.
Yeah. I asked a question, and I got some good answers on that. I wanted to play, a little game with the Win fourth stack, and got some help on that. So I wrote the PIC emulator. It is live for all opcodes. I can type assembly, I can type high level, and I type anything except conditionals. Conditionals have to be compiled because they're control flow, but everything else you can just type live and watch it execute. The fourth nucleus is common. I have the same nucleus written, and it works for either emulation or production. I have conditional compilation, so a few lines of code work better for production, written out in pure assembler. And then finally, the final pass is through generates assembly listing, just as you would expect out of a commercial PIC system. So the words we've got, kind of what you'd expect. We don't have the high-level words like word and interpret and compile and so on, because this is not an interactive system. It is a target system. So we have assembly language words, move F register to W, move a literal to W, exclusive OR, adds, and so on. Branches, and branch and skip, bit test and skip. This is bit test F register, skip on set. So it'll do a bit test, it'll skip if the bit is set. Decrement, skip, return with a literal parameter, and so on. The usual fourth words, fetch, store, dupe, nip, 2R, 0 less than, so on. Slightly higher level words for memory usage, C move, fill, erase. Then the conditionals. These are assembler level conditionals. I just put a little arrow on the end of them to differentiate them so that if they're branching in the forward direction, they have a little forward arrow, and if they're branching backwards, they have a little back arrow. And that just distinguishes them in the listings from other conditionals. The high-level fourth conditionals end with a comma. If, else, then, do, loop, begin, while. I have a not while. It turns out you have to do a double negative. Because of the limited branching facilities in the processor, I have a while and a not while. So the not while actually does sort of a double branch to reverse the Boolean situation. Finally, data structures. A PIC constant, PIC variable, and PIC array. And as we can imagine, the neat thing is, once you've got all this stuff going, if you need n plus 1, you need one more operator. You say, oh, gee, I need a so-and-so. Well, it's about 5 minutes to go add another word in. So incrementally, I can build in what's missing. So this is what the emulator looks like at the keyboard on a PC. It's the entire 128-byte memory space. These are PIC calls and file registers. The first 32 are reserved by the machine. These 16 are the loop stack. These 16 are the data stack. Down here is, and this is the top of stack. So there's the top of stack, second and stack. And this is the same numbers that are copied in. So I have 4 items on stack: top, second, third, fourth. And the stack builds up toward high memory. I put them in natural order so that this is hex 1, 2, 3, 4. Most everything else is little Indian with the little, the smaller component of an integer at low memory. But for the things I have to read during debug, I put them in natural order so it's just easier to read. And then finally up here, we tuck in some temporaries. M0 through M3 are used for math operations, multiply, divide, things like that. And then in memory are copies. This is the stack pointer, the return stack pointer, which we say is the data stack. This is an error code. A number of routines, about 20 or 30, have internal error traps. And so as the processor is dying, it shoves a value into the error code. And if it's alive well enough to tell you what happened, you get an English message. But if you died and it can't recover, you check this register, and you can see the error code that it trapped. And W is a fake copy of the W register. Over the top, for the user's convenience, we show them the status word, the carry bit, the 0 bit. This is the top of stack pointer, the return stack pointer, both in decimal and hex. The contents of the W register, and also the PIC stack is limited to 7 levels of nesting. The return stack, or the machine subroutine stack, is only 8 deep. You're limited to 7 levels of nesting, and I wasn't sure how deep my program nested, so right away I redefined colon and semicolon to count. So on execution, it just counts the levels up and down, and so you run your application, see how many levels you get down to. I think right now the maximum is level 5. And again, to put that in, it took maybe 3 minutes, I guess. When I realized I needed to count the nesting levels, modifying colon and semicolon, 3, 4, 5 minutes later, it was working. And I guess that's it. So as you type machine instructions or high-level instructions, the registers update immediately. So you can type dupe, comma, and the top of stack will move to here, and this number will push down, or will fill up on the stack. These two registers push down, and then once you're onto the machines, up to the data stack, things grow to high memory. And it's a little tricky. There's only about 4 words that actually manipulate the stack. Duplicate does, and I think anything that's added to the stack, every addition to the stack is done by duplicating, and duplicate will work on an empty stack. So if there's nothing on the stack, you execute dupe, it gives space for something on the stack. There's drop, drop to, and nip, and those 3 words removed from the stack because it's a little complicated when you're caching like this. You've got to figure out how much is in cache, what goes into cache, what goes into the actual memory stack. The processor issues. The biggest issue, well, it's actually 2 about equal. There is only 1 indirect register. This is the register you can point to another register. There's only 1 of them. Having 2 would be ever so much more useful. because you could point to the top two values in stack, or you could point to the return stack and or the loop stack and the data stack. But anyway, there's just one, so it gets heavily worked, and there's spots to store. Normally, it points to the top of the data stack, and there's a place to cache it if you have to relocate it. The carries, I wrote the whole emulator, had it all running, and then I found I was wrong because I was using classical microprocessor theory, at which when you add, you clear the carry, and when you subtract, you set the carry, you do your operation, and then the carries propagate forward. Not so in PIC. You need not, the registers are inherently either cleared or set for addition and subtraction. They're properly set when you exit an add or a subtract, but you have to propagate the carries manually. So there's three cases. One case says there's no carry that propagates byte to byte. Another one says you have a carry in but no carry out. And the third one is you have a carry in and a carry out. And there's about 3 different ways to solve that and to do it. And they are remarkably efficient. Remember that in this processor, every operation takes one memory cycle. It's 4 clock cycles, but you have one execution per, let's say, program cycle. Everything in memory is an opcode. There is nothing in the memory space that is not an opcode. There's no data in the memory space. There are no strings. Everything is an opcode. And everything executes. Okay? Now, there are ways to fool it and to make literal values that represent strings and numbers in memory. Because of the architectural efficiency, though, you can propagate the carries almost as fast as you would if the machine was processing them. So it's an irritation on program development, but in execution there's hardly any penalty. The table lookup is a little goofy. Basically, a table looks like a whole bunch of return with literal value. The opcodes are 14 bits long. If you want an 8-bit literal, you still have 6 bits up in front, which is opcode, and that 6 bits says load this literal value into the register and return. So you essentially make a subroutine call to a table. It jumps into the table and returns with a value from the table, and that's a way that you can do a workaround to get literal values. In the 18F series, then they actually have pointer registers that look into program memory space. But in this case, you're on your own. So this is what a piece of code looks like. Colon definition, it begins with a P and a P colon, P semicolon, because that's my PIC colon, semicolon, which says these will nest. These will be reporting in the nesting order. And this is just checking an overload condition. You give it a register address. The register address is preserved, and it is incremented by 4, but it's limited, or if it encounters 0 or 255, it's incremented by 4 to a limit of 25, and then at that point, it stops incrementing. Oh no, that's right. It increments to a value of 25. This is used to report signal amplitude overload on the input. I picked it because it's a mixture of high level and low level. So we have here is clear register F. The M0 register is cleared. Here is we move the contents of R0 to W, and we branch after testing a status bit. This is a machine level if, a little bit of true code, the else, a little bit of false code, another nested branch, another nested if in here, and then finally we transition to high level. Once we've determined, see, this has to execute fast. It's repetitive, it's a little error checking, it's done every loop of the program. Once we find an overload condition, then I want simpler programming and I don't mind the speed change. So now we pull up the content of the overload count register, fetch it. Literals have to be declared explicitly. I haven't changed the interpreter to actually compile numbers automatically. So whenever I want to insert an inline literal in code, I have to declare it. So for lit just compiles a value 4, which will then be placed automatically onto the data stack. So I get the contents of the overload count. I load in 4. I add it. Then here I'm comparing. I'm limiting it to a maximum of 25. I'm storing it back into the overload count. So I increment by 4 on the way up. So when I have an error condition, I get to the maximum error condition rapidly. I decrement on the way down by 1. So after I've gotten 6 or 7, once I've gotten 7 errors, I filled up my error count, but it takes 25 loops with no errors to come back down to 0. So I want to accumulate errors rapidly and clear them slowly. So in one word here, we see machine code branching, we see a mixture of high-level code and subroutines, and the fact that literals are explicit. Now we're almost done. This is a discrete logic design. This was a circa 1985 design. It's about 25 ICs. You have op amps coming in doing bandpass and limiting. Here is a switched capacitor filter with 8 capacitors. More low-pass filtering. This is phase detection. There's a one-shot that figures out from a reference time where the 0 crossings are to get a phase shift. There's a counter running up here. It goes to a latch. The latch drives a lot of LEDs. And then the counters sit over here, and this is switching your antennas. So these go, the 4 lines go up to the antenna, which is typically on the roof of the car. So there's quite a bit of stuff to that. Well, here's my design. Okay? PIC processor, bunch of LEDs, and this will likely have a hex driver in it that switches the antennas. It's just in the interest of good design because you've got long wires up to the roof. I think you could probably get away without another driver in the box. But so there's a hex driver, there's the processor, a voltage regulator, and then the input level from the receiver is 2 or 3/10 of a volt, and I want to raise it up to a 5-volt maximum scale, so I just have a simple inverting amplifier. It's offset to V over 2, so all the calculations in here go from 0 to 255. 0 volts in is 0 volts in, 5 volts in is 255. The processor, as you see, it's the F716. It'll clock up to 20 megahertz, which gives you a 5 million instruction rate per second. On the other hand, lower power if you run it slower, and I'm not in a speed problem, so I run it at a 4 megahertz clock, 1 million instruction per second rate. Has 8-bit digital converter, 12 I/O lines, costs $1.85. That is astonishing these days in processor cost. You know, back when the 8008 and 8080 came out, they were like $200 or whatever it was, and then they were $50, and then processors were $25, and then we used to buy them when I was doing this for a living. It was, you know, it was $6, $7, something like that. And now the cheapest PIC processor is about 65 cents. It's just the cost of plastic. Whatever the cost of plastic is, and handling, 65 cents, there's your processor. And it draws about 20 mils at 5 volts. That's about it. And finally, so why I came back to Forth. This is the first application I've done in 25 years. Hate to admit. I've been doing... I have not wasted the 25 years. I've done a lot of other things along the way, but this is the first true application I've written in between. And of course, why do we love Forth? Well, every word is testable. It's not that I can't do breakpoints or do tracing, but I don't need to. I mean, you can just test every line, every word. You make a change. You know, I have a little test suite. I have about a 75-line test suite. So anytime I change the application significantly, I can just run the test suite as just 75 lines of code, and it just sets up processor conditions and checks to make sure that proper responses occur. And the good old, and the F12, when you're running the editor on the Win4, you just push F12 and it saves the file you're working on and compiles it, and you're live in half a second. Just about as quick as you can just hit the button and get back to the keyboard. You've got your application live. It has the, what you see is what you get editor, which is great. A very, very rich environment. And another thing that's, for example, I found just the other day, there's a bracketed if then else. So you can do high-level conditional interpretation. If you're doing conditional compilation, you can just intermix instead of if then else at code level. You can do square bracket if then else, and you can interpret Booleans to selectively interpret or compile code. And I just discovered that just looking around. Well, actually, I was reading some Andrew's code, and I saw it, and I figured out right away what it had to be. Another thing that's absolutely beautiful about it is they haven't changed it in 15 years. So it's stable. It's the same thing. Whatever you see now is what was in 1996, and they dated the changes. There actually were a very few little things that were done in somewhere around year 2000 in a little bit, but all the core stuff was stable from 96 on. And anyway, so that concludes my formal remarks. Do we have any questions? Yes.
I noticed you also had a thing that calculates when you have an overload.
Yes.
Have you ever considered adding automatic gain control?
I do. I do. Do I consider having automatic gain control? I do. I have an 8-to-1 dynamic gain control, but when you're outside of the gain control, outside of an 8-to-1. But do I consider doing it in hardware? See, I do the automatic gain control in software. Do I consider doing it in hardware? No, the answer is no. One reason is I'm out of I/O ports, and the other case is if you're doing, you kind of need an analog signal externally to do the gain control. And I'm sitting there with this thing in my hand, and I got a knob right here. This is the gain control. So all I do is turn it until the lights don't flash anymore, and I'm live.
Well, what I mean is you could also extend it into another PIC processor since they're 50 cents a pop, and some of these PIC processors are very, very small. They're just like a controller, and
So the polite answer is no. Okay. Here's what one looks like. Again, Andy has one here. It's your typical box. This has got, looks like it's got 32 LEDs on it. 16 LEDs, and it's got a calibrate, damping, and audio level. The calibration is required on these classical ones because they're using analog detection internally. They're using sort of a phase shift determined by zero crossings. And okay, I don't think I need to do that because I am, it's
Sorry to cut Bill
quite
off.
analytic.
We've got to get on
Good.
with the show here. If you have